The light tracker comes in two parts, a headpiece and a display monitor. The headpiece is designed to be attached to a cap using a clip. To turn it on, press the white button on the side, and the green light will indicate when it is on. To access the battery, simply slide the door off. The display monitor can be plugged into a wall outlet. To turn it on, flip the switch on the top. A startup screen should appear. When the headpiece is turned on, pointed towards the center red dot, this will start the tracking. Once you are finished, simply turn off both parts.
The head mount was designed using SolidWorks, and it was designed in two parts. The head mount, which includes a hat clip and a sliding door with added ridges for better grip. Our display enclosure features an ABS box for our wires and electrical components. Additionally, we catted two mounts for our 16x16 LED matrix. The main mount, which has small cutouts, accommodates for the resistors on the matrix, so the matrix fits nicely into the mount. An additional frame was added on top where a thin piece of paper can be slid in, which acts as a filter for aesthetics. All the catted parts were printed out of PLA, and our sensors and LED matrix frames are screwed onto the ABS enclosure. Holes were also milled on the enclosure for wire access.
For the wiring, the head tracker consists of 6 IR lights, a green LED light, and a button, all wired in series with a 9-volt battery power source. For the display, a 12-volt 5-amp power supply is connected from a wall outlet directly to an Arduino Uno within the enclosure. The Arduino outputs 5 volts to the LED matrix panel and the 4 sensors, utilizing breadboard connections. The LED panel's 5-volt and ground wires connect directly to the breadboard, and its data input connects directly to the Arduino's digital output pin. Each sensor has 6 pins connected to the breadboard. The sensor output is connected to an analog input on the Arduino, and a 56 mega ohm resistor is wired between the sensor's output and its internal resistor, which increase the sensitivity of the sensor.
To start, we labeled each of the sensors. Let's call them A, B, C, and D. We needed to convert our sensor readings into a coordinate position. To find a position along the x-axis, we found the difference in sensor readings between the horizontal pairs of sensors, that is, A and B and C and D. We then added these values together and divided by the sum of the sensor readings. This gives us an average x position. To find the y-axis, we applied the same idea but used the vertical pairs of sensors instead, which is A and C and B and D. Finally, we applied a linear fit formula which converted our average positions to a number between 0 and 15. Once we rounded these values, we got our coordinate position. The x component corresponds to which column the user is looking in, and the y component corresponds to the row.